Good afternoon, Professor. Could you help me solve a problem?
Sure, Billy.
Thanks. Okay, Jimmy and I like to play on a seesaw. Jimmy is 210 pounds and I only weigh 140 pounds. If I sit 6 feet from the middle of the seesaw, how far does Jimmy have to sit if we want to be balanced? And by helping me solve this problem, I mean assist me in gaining a conceptual understanding.
No problem. Let's start at the very beginning. A seesaw can be modeled by a lever. A lever is a weightless beam that leans on a balancing point called the fulcrum. The distance from the fulcrum and the weight is the lever arm. Let's try putting a weight on the lever to the right of the fulcrum and take note of what happens.
The weight causes the lever to rotate clockwise.
That's correct. Aren't you a little Einstein, Billy? What happens if we move the same weight further out?
The weight has a greater clockwise effect.
Correct again. Let's keep the distance the same but replace the weight with a heavier one.
The greater weight at the same distance has a greater effect on the lever arm.
We call this effect or moment of force on the lever torque. Torque is a type of force, an influence causing our lever to undergo a change, to rotate an object, in our case a weight, about the fulcrum. Torque can be thought a rotational force moving about a pivot point. Knowing this, what type of torque would occur if the weight were placed to the left of the fulcrum?
It would have a counterclockwise torque on the lever.
Correct. Since the weight is placed on the left side of lever, we will have a counterclockwise torque instead of a clockwise torque. Moving forward, now what do you notice when two equal weights are placed at equal but opposite distances?
It's balanced.
Yes, it is, and we say that the lever is at equilibrium. Okay, now let's try to moving both of the weights directly in the center of the lever stacked on top of each other. What do you think will happen? Will the lever remain balanced?
I think so. Because the weight will be balancing on the fulcrum and not on any of the lever arms, so the lever arms will remain at equilibrium.
Try it out.
I was right. Yay.
Yes, you were, for the exact reason that you said. If you place both weights at the midpoint, there will be no torque acting on the lever arms, and they will remain undisturbed. Also, if we put a single weight exactly at the midpoint, we will still have this equilibrium.
But wait, why does distance and weight affect equilibrium of the lever?
Well, in order for the lever to be at equilibrium, then the weights and distances must be proportional. Meaning that if on one side of the lever the weight or the distance changes, then the other side of the lever must change either the weight or distance to keep the lever balanced, or rather to keep the relationship between the two lever arms constant. Understand?
So, for instance, if I have two weights, one that weighs 2 times as much as the other. Since we have half the weight on the left lever arm, can I try moving the lighter weight twice as far away in order to keep the lever balanced?
Why did you want to move the lighter weight further away and not the heavier one, since it is twice as heavy?
I moved the lighter weight because if they were at the same distance, then there would be a clockwise torque on the lever. Therefore, I needed to create a greater counterclockwise torque on the lever. And I did this by moving the lighter weight on the left side outward twice as far so the lever would be balanced.
Okay, perfect.
I was right. No, I was right.
Yes, you were. Do you think you've gotten the concept of torque and how to find the equilibrium of a lever?
Yes.
Okay, so what if now we had a weight, W, on one side and 2/3 of the weight, W, on the other? What would be the ratio between the distances?
Okay, first, the distances cannot be the same because the lever would not be balanced. So, since there is a greater counterclockwise torque on the lever already, we need to make the right lever arm have greater torque to keep them balanced. Therefore, if we kept the same ratio that compared the weights and applied it to the distances, the lighter weight 2/3 W would need to be 2/3 closer than weight W.
Does that work? Let's see if the lever is balanced.
It's not. Oh no. What did I do wrong?
Well, let's see. You explained that if the ratio between the weights was 2/3, the ratio between the distances must be 2/3. However, the ratios are in fact inversely related to each other. This means that when an aspect, let's say weight, on the right lever arm is less compared to the left lever arm, creating a counterclockwise torque on the lever, we must have an inverse ratio creating a greater clockwise torque on the right lever arm to balance the lever. This creates the right lever arm have a greater distance than the left lever arm. Therefore, the ratios need to be inverses of each other. Do you understand?
Oh, okay. This would mean that if the weights are 2/3 of each other, then the distances must be 3/2 of each other for everything to be proportional and balanced. So we must balance the lever by representing the weights and distances inversely proportional to each other.
Yes, exactly. So let's go back to the problem at hand.
Okay. So my problem is that Jimmy and I cannot balance ourselves on a seesaw. Jimmy is 210 pounds and I only weigh 140 pounds. If I sit 6 feet from the middle of the seesaw, how far does Jimmy have to sit if we want to be balanced?
Okay, let's draw a picture. Pictures help.
Well, Jimmy, although rather large for a second grader, is 3/2 heavier than I am. So, since we need our weights and distances to be inversely proportional, that would mean that if I sit 6 feet away from the middle, then he would have to sit 2/3 closer to the middle than I would.
Exactly. Now, what would your answer be?
Well, 2/3 of 6 is 4. So he is to sit 4 feet away.
Correct? We can also represent this relationship by an equation. The weight times the distance one lever arm must equal the weight times the distance on the other. So our equation is W1 times D1 equals W2 times D2.
An equation.
This equation can also be written W1 divided by W2 equals D2 divided by D1. This new altered equation explains the concept of the relationship or ratio between the weights must be equal to the inverse of the ratio between the distances.
Oh, well, why didn't you tell me that in the first place? I could have just used a procedural equation this whole time. Oh no, now I understand how ratios work conceptually. Thanks, Professor.
You're welcome, Billy. If you have any more questions, feel free to ask.
Okay, thanks again. I want to go tell Jimmy and try out our concepts of torque and equilibrium on the lever now. I mean seesaw. Bye.
Bye, Billy.